Yep.
All right, welcome everyone to the fourth direct write lithography workshop and its reactive ion etching webinar series. Welcome to webinar number 2 out of 6. Before we start, I'd like to do a few acknowledgements, starting with the acknowledgement of country. Sorry, let me restart that. I wish to acknowledge the people of the Kulin nations on whose land we are gathered here today, and I pay my respects to the elders past and present. Then, of course, I'd also like to acknowledge, the Australian National Fabrication Facility and CEO Jane Fitzpatrick for their ongoing support, and all the panelists, and especially for this webinar, Jörg Hübner from DTU, who is also on the call. Thanks for facilitating the next two webinars by Henri Jansen. And of course, the whole organizing committee, a team for their ongoing effort to put this strong webinar series and hopefully workshop together as well. And this brings me to our presenter today. It's Henri Jansen from DTU. Henri was born on the 17th of May 1962 in the Netherlands in a town called Marienheem. I hope I pronounced it correctly. At the
very good.
Eastern countryside, inhabited with more cows than people. Sounds like my hometown as well. As a kid, he joined the dangerous social Dutch soccer events, and after being hospitalized 2 times, he decided to try his luck with single-person sport events like long-distance running and cycling. After doing military service in the Dutch Royal Navy between 79 and 85, and having seen many astonishing sceneries abroad, he started his academic career. From 1985 to 1991, he did his master's in science study at the University of Twente with special topics in quantum physics and material science. In 1996, he got his doctorate degree in, and now in quote, and now for something completely different, unquote, under guidance of Professor Dr. Jan Vloetman with the thesis Plasma Etching in Microtechnology. From this topic, he became locally well known as the Black Silicon Man. Then he entered for 2 years the dark side of his academic career to develop plasma engineering in the industrial environment. In 1998, though, he rejoined the academic playground to give assistance in education and microengineering at the University of Twente and was promoted to become associate professor in 2003. Then in 2016, he took the final rung of his academic ladder to become full professor at DTU Nanolab, where he continues to play as full-time plasma engineer until today. He has been supervisor of numerous students over the past years, resulting in 120 plus publications that have been cited over 6,500 times and causing an H index of 42. So with that, I hand over to you, Henri.
Yes.
Please share your screen and let's start with the webinar.
Yes, thank you. Okay, now the mouse.
Yeah, we can see your screen.
Yeah, and we have the pointer.
Yes.
So good morning, also all of you. Thank you for the nice introduction. As you know, we try to go and to talk a little bit about plasma today. And before I can really go to the plasma, my lecture is going to be partly also about gas dynamics, so what's going on there. So that will be let's say the first 20 minutes. And let's say then the break is a little bit too early there. Then I start with the plasma fundamentals, where I talk a little bit more about the Paschen itself, plasma oscillations and plasma potentials. And then after that, in general, I would say what I'd like to try to do is that the first part of the session will be taking roughly 40, maybe 45 minutes, and then you have a 5 minutes break. And after that, I will continue with the last part of plasma fundamentals, after which you can ask any in-depth question and try out if I can answer that one. I might run away if it's too much. But there's a little bit the idea, and then the second session that will be then the 11th of December, it will be coming a little bit more into the real world of etching, where it is fundamentals on exactly chemistry and the profile, how to control it. And then finally also some real experimental results. So you can see that if you understand all the previous stuff, then you should be able to understand also the final steps of, let's say, the Bosch process, the DRAM or the core. Why are we doing what we are doing? So I think it is important to have all the basics there. And although you can find it on the internet, you will see always on the pages at the bottom side somewhere lines. So it will be here on that line that are clickables. And these clickables will always provide you more information. Typically, it's to the Wikipedia, because that one is the only one I consider to be stable enough that you can always click and get some information instead of unknown source or whatever. With that, I would say, let me start for my first, let's say, 40 minutes of talking. And hopefully you will enjoy it. Okay. Don't do this to me. So now my pointer is not. I will do it. Okay. Yeah, now it's working. Good. What are plasmas now? Ordinarily, we hardly encounter plasmas in our daily life. Matter, which is normally seen, exists in the solid, liquid, or gas phase. But lightning and auroras appearing in the polar regions are plasmas in nature. And all stars, including the sun, are masses of high-temperature plasmas. Also, the interstellar matter and nebula are in the plasma state. So it has been said that the greater part of the universe is in the plasma state. But plasmas can also be artificial. Man-made plasmas, or electrical discharges as they are called, are accomplished by using a glass tube with 2 metal electrodes installed. Then evacuating the tube to a pressure between roughly 0.1 and 1 millibar. It can be a little bit different, and applying a high voltage between the 2 electrodes. Now, as the voltage gradually increases, that is here, only a small current flows. But when the voltage has reached a few hundred volts, typically, current through the tube shows an abrupt increase, and the tube begins to emit visible light. That's where the plasma is born. Now, a plasma contains a high density of charged particles and is therefore highly conductive. It's exactly this difference what distinguishes the plasma from the normal gas. And it's also sometimes called the fourth state in which a material can exist. Now, the simplest plasma discharge uses a direct current, or DC, voltage source. The high electrical field effectively converts electrical energy into kinetic energy, mainly for the electrons. So they are going to be accelerated here in the field which you apply between these 2 electrodes. Now, under the correct condition, these electrons gain enough energy, high enough to ionize gas that liberate additional electrons. So here you hit maybe a molecule, and it continues its own trip, but also it created one extra. So these fatal collisions create an ever-increasing number of free electrons while passing towards the positively charged anode, and in the end forming a plasma. Now, plasmas can also be generated using a radio frequency, or RF source. This enables us now to install electrodes with insulating surfaces. This type is called capacitively coupled plasma, or CCP. Another possibility is to use a coil wrapped around a glass tube and excite the discharge electromagnetically. And this type is called inductively coupled plasma, or ICP. There are more, but for this story, it is, it doesn't matter how many types there are. So ECR and magnetic enhanced, it's all fine. But these are the main, let's say, players, I would say, the CCP and the ICP. Good, we already talked about it. Now, to understand how a plasma comes into existence, I would say it's unavoidable to understand the ideal gas first. Now, the ideal gas consists of molecules of mass m and diameter d in ceaseless random motion. The size of the molecules is negligible in the sense that their diameters are much smaller than the average distance traveled between collisions. Finally, the molecules do not interact, except that they make perfectly elastic collisions when the separation of their centers is equal to d. I will come to that directly, what that means. Now, the ceaseless motion of gas molecules is accurately described by the Maxwell-Boltzmann, or MB, speed probability distribution function, PDF, and formulates the probability F of a particle speed V being near a given value. It depends on the temperature T of the collective, the mass M of the particle, and the specific speed where we are looking at. And that's this equation where you can see this is the Maxwell-Boltzmann, the general form. Now, this one is arrived from common sense arguments like symmetry and ideal isotropy by Maxwell, and later on, or meanwhile, I don't know exactly, proven rigorously by Boltzmann. Please check a little bit more on Wikipedia then here for the Maxwell-Boltzmann. They explain how you get it from this common sense. It's quite beautiful how he explains it and how he could drag this out of the result. If you see it now, you would say straightforward, but to get this idea, it is by way a very big challenge and an accomplishment. Doing this, you can see, because it depends on the mass M, you can see that here this Maxwell-Boltzmann distribution speed, that for the smaller mass, they are faster, and therefore their speed, or the maximum speeds, are much higher than for, let's say, the bigger molecules with a bigger mass. Now, with this Maxwell-Boltzmann PDF, we can now define the following speeds. First of all, of course, the most obvious one is where we have here where the function is, let's say, 0, the derivative of the function. This is the most probable speed, V and P. And putting that into this equation is really not difficult. You can find it in the Wikipedia. You can calculate directly. It's the square root of 2kT over m. And as we just saw before, the lighter the molecule, the faster it will move. Then we can also define the mean or average speed. This is by convention, let's say average values are presented by the chevrons, what you can see here. This one is a little bit more if you calculate. And finally, we have the root mean square speed. That's the, let's say, the average value, but then from the squared velocity, but then you take the square root. And it comes even a little bit more. Why these two are, let's say, separately is typically this one you use for flux and so on, where the velocity and momentum is our main target to understand, whereas the root mean square speed is in fact directly linked to the kinetic energy. Of course, that's m speed squared, or half times it. Good. But now using the most probable speed, so we just arrived, we can normalize the function. So we go back to the Maxwell-Boltzmann and we fill in that the most probable speed is the square root of 2kT over m. We see that over here. If we then fill it in and we define a new parameter, capital gamma, then we get this equation, what you see over here. Now, what is the fun about this one is that now suddenly all the curves have been merged into one. So all the noble gases there's nothing anymore, because all that information is gathered inside this capital gamma function. So this curve means that it's always the same. And by default, the maximum is at 1. Gamma is 1 because at that moment, this function here is 1. And so then they are the same at that moment. Good. Now, as we come back to this normalized function later on, because it makes calculations much easier. So if you will always use this one, so the usual one, then you always have to take into account high numbers, so the mass and the temperature. Whereas if you use the gamma function, you can calculate everything, and just in the final stage, you put in the mass and the temperature. So it's less prone for making errors. Now, as a result of the Maxwell-Boltzmann, the mean kinetic energy, and we just talked about it, because that is the speed, the RMS speed, the square root of the 3kT over m. But now the mean energy is, or the kinetic energy is half times the mass times this RMS squared. We fill it in, but we just from a maximal Boltzmann and we find 3/2 kT in joules. You can also divide it by the charge, unit charge, and you get it in electron volts. For instance, at room temperature, 293 Kelvin, 3 kT/2 is roughly 0.0388 electron volts for gases. There's a little mark here. Read later. I will not treat it here. It's only, let's say, it's a little bit of danger zone. So in physics, they define a little bit different. But let's say you can find it here more, and then you check here. You can still see it, I guess. But now in plasmas, however, the electrons are accelerated up to much higher velocity due to electrical fields. We just saw it. And they have a very small mass, and therefore they will be speeding up much faster than any gas molecule or ionic species. So there's then no equilibrium between these various particles. And therefore, the temperature and the Maxwell-Boltzmann PDF are described respective to these corresponding particles for the inside your plasma. For instance, for S6 plasma, having for maybe a gas temperature of 300 Kelvin, so that's around room temperature, this would mean 0.039 electron volts. But the ions, although they don't respond very big to our radio frequency source, they will a little bit, and they get a little bit hotter. It's 500 Kelvin maybe, somewhere there. It can be different, so you can tune with it, but to have a general idea. And the electron temperature for sure is much higher, about 15,000 Kelvin and more. And that one cannot just go lower. And the reason for that one we will directly see, but it has to do with, in order to have a plasma, we need ions, and therefore we are sure that there are, let's say, a lot of excitation levels, because we have ionization, and excitation is even easier than, let's say, ionization or dissociation. We will talk about that in a minute. Next topic is the pressure. Now, after the temperature, we also look at the pressure, because also that one can be found from the Maxwell-Boltzmann now. So now when you have a collection of particles with random velocity is put into an enclosure, of course, they will collide all the time with the walls. Now, each time a molecule hits the wall, I make here a little sketch, then it will exert a force, and the total force per unit area due to all these molecules is known as the pressure P. So here it will hit, when the molecule will hit your surface, there will be a momentum transfer, and it will be, because let's say the momentum, so that is mass times the velocity in the x direction, it will be transported, it will be reflected, because we said it is elastic, and therefore you have a change in impulse moment of two times that value. Now, we also know that in fact, the velocity, if we call it now velocity, it's a vector. And it means that at x, a y, and a z direction. So therefore, for a vector, we know that we just can add them up and take the square root. So then we would get the speed. So that is velocity irrespective of their direction. But we know now, because Maxwell assumed that the gas is isotropic. So it means that let's say the velocity in the x direction and in the y direction and the z direction are identical. So we can as well write it down as Vx squared. So it is 3 times, because we have to add all these 3, because it's a vector. Then we know that, so the pressure now is the force per area, and we can fill in that this momentum, that's 2 times this change in momentum per unit time divided by area. And then please go to the Maxwell-Boltzmann theory, because this star here is a little bit more than what I show here. And it will add up, but it's not difficult to follow. You just have to know integration of sine function and cosine function, but that's fine there, I guess. And these numbers coming in here, after doing some calculations, then we can fill in the Vx squared being directly related to the root mean square speed. And because we know that one from the previous slide, it means all things glues together into NKT. And that's beautiful, because this equation now, P is NKT, is of course a key result of kinetic theory, because it connects now the perfect gas idealization to the kinetic theory, to the ideal gas approximation of thermodynamics. I think that has been the big one. So now everything was explained. At room temperature now, 293 Kelvin, and pressure, that's 1 atmosphere, let's say about 10 to the power 5 Pascal. It means that the density of gas, when you use that here, this formulation, is about 0.025 per cubic nanometer. So there's about 1 molecule inside a volume of 40 cubic nanometer. If you look, for instance, then for at 1 atmosphere, if you look, for instance, for the silicon as a solid material, they're about 50 per cubic nanometer. So they are 2 times more dense than its gas form. That's also important to understand, because later on, when we go to the plasma chemistry, this is entropy, the change in entropy, and this can be used to calculate what is the chance and that, let's say, a certain gas will be, or a certain product, plasma product, will be a vapor. We are using that. Now, similar now for the flux or current density. Now we are using, because it's a flux, we are interested in the momentum, or in this case, velocity, average velocity. This phi, I think it's phi or something like that. This phi is a quarter. Again, you can calculate this one with kinetic theory of gases. You can also see that in Foresight Kinetic Theory. It's a very nice homepage over there, where it's going a little bit deeper than kinetic theory. And I would say it's great to read all the things they have already put down in lectures. But you can now, again, fill in the previous results from the kinetic theory, and it is pressure times over the square root of 2p mkt per unit area and per second. But we can now also try to calculate the currents inside the plasma bulk, because we know the average speed is the square root of AT over pi times m. Then for the electrons, we fill it in, and we get the average speed of the electrons, and for the ions, it will be the average speed of the ions. Now, for plasmas, it ought to be neutral, and also we see that later. It means that the density of electrons and the density of ions should be the same, or roughly the same. This means that we can now make the ratio between these two, and if we do so, many of these things just fall away. They drop away, and we end up with, I don't want this one to be, that's the current arrived from the electrons divided, or the ratio between the current of the electrons and the ions is approximately 3000 for the SF6. For other gases, it will be a little bit lower for argon, but around that value. But please remember now that this is for currents inside the plasma. So that means that the plasma glow, there are no charging objects or walls considered here. Then this is true. However, for currents outside the plasma, so the plasma sheet, or when it reaches an object, we must consider the shielding effects. So that these objects will be charged, and they will repel the next currents which coming in. That's expressed by the Bohm velocity, and we will arrive at that a little bit later. Now something about, okay, we have pressure and we have temperature. Now we should also say something about that all these molecules, they move around, and we know that we would like to have a hit between the electron and the gas molecule, because we would like to have excitation, dissociation, or ionization. So we need to be a little bit more about collision frequency and molecular cross-section. Now assume a container is filled with molecules having diameter dt, d2, you see here all of them, and with the density n2. And suppose all these molecules d2 are at rest, but one molecule, d1, here, is rushing through the volume with an average speed of 1. Now a collision occurs whenever the distance between these centers becomes d12, here you can see, smaller than the diameter of these two divided by 2. Now this moving gas molecule, d1, will then sweep out here in unit time a cylindrical volume of pi times this diameter squared. So this is just the circle area times this velocity of this molecule. And we define this one as the cross-section area of this sweeping volume. Just for the collision frequency, now we need to multiply this with N2, so then we know how many in this volume would be hit. But now, in fact, these molecules D2, so the other collection, they are moving too. And it's the relative velocity between D1 and D2 that matters. So in fact, a expression for the collision frequency should be F12 is the density of N2 times this collision cross-section times the average speeds between 1 and 2. Again, this is a factor, and now there are two of them, and we have to, again, add them by the square and the square root of the, so the root mean square value of this. But now for only one gas, we know that the average speed of 1 is identical to average speed of 2. So we add them together and we get the factor of 2. So before that, we got 3 times, but now we, or one third, you could say. And now we get, because of this, we have now the velocity or the speed. It will be the square root of 2 times the average speed of the gas molecules. And you can also go back and see that, in fact, sigma 1,2 now is, if they are identical, it is the sweeping area is 4 times the cross section of this molecule. So that's why you see 4 times. And this is now the molecular cross section. So finally, we can get that the collision frequency of the gas with its own gas molecules is the density of the gas times its cross sections times its average speed times 4 times square root of 2. Now, because the electrons, the average speeds of electrons is much bigger than the average speeds of the gas, because it was driven by the electrical field, which is only, let's say, mostly accelerating the electrons. If you take that one in here, you would see that, of course, the other one, if you look at the electron, the other one is neglectable, and you don't get this square root of 2. But also because now suddenly your electron is much, much smaller than your gas molecule. So if this is an electron, they are in a way the same, the sweeping out area with respect to the molecular cross section. So also the factor 4 is gone. It means that the collision frequency of the electrons is about 4 times square root of 2 is about 5.5 times less. Now you can calculate with this that the average speed and the density and collision cross section for example, nitrogen, we can calculate that it can be roughly 80 kilohertz at 1 Pascal. Good. Now, knowing the collision frequency, it's very straightforward to calculate the mean free path. It's simply the average speed of the gas molecules divided by the collision frequency. So we just fill in what we just got, and it is 1 over square root. So that's what you see here. And for the electrons, because they are much smaller and much faster, this factor of 4 times square root 2 doesn't exist. So that one will travel. The mean free path is about 5.5 times larger. So remember that a little bit, that the electron goes further. And we can also define the collision frequency per unit density or the rate constant. So that is in a full collection how many times particles collide with each other. So that's cubic meter per second. This one we will use later on for calculating the electron temperature. We can now take in all the numbers, and as soon as we know also the diameter of the molecules, here we can calculate these other values directly with kinetic theory. To calculate and to find the diameter, there are a lot of studies, and it's a little bit tricky, but you can take them from standard, let's say, tabulations, and fill then in these numbers. Then for nitrogen, if you then take that number, you can fill it in the Maxwell-Boltzmann theory, and you would find that for nitrogen, the mean free path at 1 bar, so 10 to the power 5 Pascal, is about 58 or 60 nanometers. Remember that one too. Comes back directly. Let's now go to, let's say, what's going on when we have a collision. So now we know the collision mean free path, and we know the collision frequency. We know, let's say, the density of these collisions. What happens if it collides? Now, by conservation of momentum and energy, the fractional energy E transferred from mass 1 to mass 2. So consider here 2 molecules, and one is hitting the other one. Then this transfer of energy will be 4 times m1 times m2 divided by the square of both added together. Now, when the collision is, when you look at this one, when the collision is frontal, then m2 in this expression has its maximum value of A. So then you will export all the energy. We know that when from billiards. So when you have a ball on your green field, and another ball is coming in with speed, and the other one, this one is at rest. As soon when you have a full hit on the knock, that one will stand still afterwards, and all the kinetic energy is going to the other one. Now, there's a difference now when an electron will hit an SO6 molecule. So this is when SO6 hits SF6. It's just elastic, and it will be transferred a lot of energy. But for the electron, because it's so small, if you fill that in this small number here, it's much smaller than SF6. It means that it just bounces back. It cannot do anything. So it's like a little ball hitting a truck. It will just bounce back. The truck will not be impressed by it. This here you can see the proof. I make it white because I think it's not wise to talk clearly, but please take notice from it, and you can prove it. It's a very nice and neat way of proving this formulation here, where we have this conservation of energy and momentum taken together. But now we could go also to the next. Let's say now the collision is inelastic, so it is not bouncing easily. So what is that, for instance? That could be that we have here a mass 2 and a mass m is hitting it, but they merge. Of course, that means this is not elastic anymore. They will travel together with a new, let's say, speed and kinetic energy. If you do that, again, we are going to calculate this one, taking the same laws of conservation. Then we find it is m2 divided by m1 plus m2. Now suddenly, whereas the maximum elastic energy transferred from an electron to an SO6 molecule was close to 0%, we just showed that before in the previous slides. In this case, when it's inelastic, when it just rises, it can go up to 100%. So for instance, so an electron who would hit a molecule with enough speed, it will lose all its energy. And the other molecule will either move much faster together with the electron, or if the electron separates, it might be that you get an excitation or ionization. And that's, of course, the whole idea. Now, consequently, so electrons driven by the RF generator will lose their kinetic energy mostly by these inelastic collisions. And will only slightly raise the gas temperature. Because we saw that it is, when it's smaller and we have an elastic collision, nothing will happen. This is why they are frequently referred to as cold plasmas. So the electrons are very hot, but let's say the gas molecules stay cold, and the ions too. So that's what we just showed before. Electrons could be up to 15,000 Kelvin, whereas the gas and the ions are maybe 500 Kelvin and less. And here is also, later on, you can look at it yourself a little bit, the proof for this inelastic collision. Good. Let's continue with plasma ignition. Now, because we know now enough from the gas fundamentals to understand what's going to happen with when we create a plasma. Now, the simplest plasma discharge uses a directed current or DC voltage source. The high electrical field would effectively convert electrical energy into kinetic energy for the charged species. Initially, there will be always a few ions and electrons inside the plasma, inside the gas, sorry. The ions may gain enough energy to knock out electrons at the cathode after impact. So when an ion is somewhere here moving and it moves to the cathode, it can extract an electron from it. This is called the efficiency of the ion impact. It can be around 0.01. You have to think in that kind of numbers. Of course, this depends on the cathode material, the type of ion, and the kinetic energy of this ion species. Now, ionization will happen when these free electrons gain sufficient energy to liberate additional electrons after a fatal collision. We just talked about that in the beginning. Now, if the number of collisions between the opposing electrodes is sufficient, effluence will cause a plasma to develop. Now, a good way to predict the ignition and sustainability of such a plasma is the Paschen curve. It shows a pronounced minimum for the breakdown voltage. Here's the breakdown voltage versus the pressure P between two electrodes separated by a distance d. This is the Paschen equation where most of the numbers are just mathematics, but A is a constant related to the mean free path, B is as a constant related to the ionization energy, and gamma is the just already mentioned ion impact efficiency. And they are different for, this is mostly different for the cathode material, and these two are more different for the specific gas we are talking about. Looking at this, so that if you have now, for instance, a gap of, because it's written here, pressure times electrode spacing, and we directly say why we do it like that, in torr centimeters. So if we see that here for argon, the minimum is around 1 torr centimeter. If it would be a gap would be 10 centimeters, then the argon minimum is around 0.1 torr, because 0.1 times 10 is 1 torr times centimeter, or 100 millitorr. So for a gap of 10 centimeter, I would expect that the minimum is around 100 millitorr for argon. For air, you can see it's a little bit lower. It's about 75 millitorr. Now, starting somewhere, let's say, assume we are somewhere here in the lower side of let's say the plasma where it is already sustainable. This here is the Paschen curve, but we are a little bit higher to make sure that we have a plasma. Now, starting from this minimum, if we now lower the plasma, the pressure for a fixed distance, then the number of collisions will decrease. Because we have less molecules. We just arrived at that it is the number density of the gas who is saying how much is your collision number of collisions. And that means that because we have less collisions, the effluence is compromised. We don't have sufficient number of collisions anymore between the cathode and anode to create a huge number of free electrons. Now, if we instead increase the pressure, what will happen is that instead, because the electrons are colliding with the gas molecules more and more frequently and faster, it means that they didn't gain enough kinetic energy in between the two collisions. And again, and in this case, the ionization is compromised. So this is why you see that there's a minimum where at the lower side, there's not enough collisions to cause effluence, and at the higher side, there's not enough energy available to cause ionization. So if we check for this curve, now try to understand that if the pressure is doubled in this situation, but now at the same time we halve the distance. So what we did is here you see we halve it. Then in a way nothing changes for the plasma bulk. This is because the electrons now gain the same amount of energy in between two subsequent collisions. Yes, the distance is smaller, but because we have now the electrical field is higher, we have compensated for that. This is why the breakdown voltage is plotted against the PD product, what we saw here. Moreover, at higher PD values, where the number of collisions is sufficient, if the pressure is now doubled, and at the same time we double the voltage for a fixed gap, so the electric field is doubled, nothing will change. Again, this is true because the electrical energy gained in between collisions stays the same. So this is a little bit an explanation why the Paschen curves is here a minimum and why it goes to be more like almost linear in that direction. What is now the effect of this talk, of this story? Let's go back to the one you had to remember. We have for nitrogen a mean free pass at 1 bar at 1 atmosphere of roughly 60 nanometers, 58 nanometers. We found that. So the mean free pass times now the pressure of the gas is 58 nanometers times 10 to the power 5 Pascal. That's roughly 6 millimeter Pascal. And for the electrons we knew, also had to remember that it's 5.5 times more. So it's around 33 millimeter Pascal. Now have a look at the Paschen curve. Here's the breakdown voltage again, and here's the PD. So the pressure times distance product. For the nitrogen, it's around 0.1 kilopascal centimeter. And if you check with the previous one, it's correct. It's the same number. Taking that one, so that means 0.1 centimeter kilopascal, but that's the same as kilopascal is 1,000. So 1,000 times this one. So it is 1,000 millimeter Pascal. So that's my mean free pass times pressure. And this is how far the electron will reach. So when we now divide these two, it means that we have 1,000 over 33 is in our gap. We would have 30 gap collisions. And every collision will create, because that's what we let's say we're aiming at, it will create an extra electron, roughly. So it means that it doubles every time. And because we have 30 collisions, it means we have 2 to the power 30, and that's roughly 10 to the power 9. So 1 billion after a while, after leaving an ion who has hit the cathode area, where gamma is maybe only 0.01, that electron that comes out will have, when it goes to the other side, after it comes close to the anode, it will have been creating 1 million extra electrons. Well, that's sufficient for the avalanche, because that's why at that moment this line, the Paschen curve, is starting with where the plasma is started. I hope this is understood. But now let's make it even funnier. Like with the Maxwell-Boltzmann, we did a trick to get it. We did some mathematics to get it normalized. We can do exactly the same for Paschen. So we go back to the original equation, and we can find now where, let's say, this curve is, let's say, where the derivative is 0. There we find our minimum. And you can directly take that from this one, and you find it very easily that this is for the PD minimum, and this is for the breakdown minimum. But now, just like the Maxwell-Boltzmann PDF, we can convert this into a normalized version. So what we say, we take A and we convert it into alpha over. We divide it by P times the mean free path of the electron. And we do the same for B by multiplying it by the ionization energy. If you do so, you just fill it in, then you get this function, where now the minimum of T over gamma E, that's our new, let's say, parameter, is what you see over here. And 1 plus this ionization, 1 over ionization, and ln function, and this is the number of Euler divided by original alpha. And here we get the minimum. But they are both, let's see, you can see, both normalized. If you do so, you will find that alpha and beta are fairly or almost completely molecule independent. And I have here a table, you can look that up later, but is only to show that if you do so, and you do this normalization for, let's say, all the gases, the Paschen curves of helium, neon, xenon, and you do this normalization, they just come together. So they come into a single one. And the line on which it falls, which is depending now solely on our ion efficiency factor at the cathode, that's the only one which can shift it. So when the gamma is very small, it will be higher, and the better your gamma, so the more electrons the ions can directly hit out of the cathode area, the lower these curves will be. But for the rest, if everything is for the rest identical, they should stop. They will be on top of each other. And you can of course understand that the higher the gamma function, so the impact, the lower the PD value. So then it means that you really drop the minimum of the Paschen curve to an easier way. So it's easier to get breakdown. But we are not directly always working with DC. Many times we're working with RF, so the radio frequency source. And now something special happens, because with the DC, the cathode is needed that the ions impact and that they create a lot of electrons while passing by the plasma to the other side. But for the RF, in a way, all the time the field is changing up and down and up and down, plus and minus, plus and minus. So in a way, you keep the electrons inside, because here in the DC case, the electrons will die at the anode. They are gone. But here, before they reach the other side, they are returned. And all the time, they gain energy from the RF source. In another way, when you would look, the electrons would move maybe, and just not hitting the cathode or anode area. But the ions, where let's say then here, of course, when they go up, they convert, so the kinetic energy is low, and here again, they speed up the electrons. So most of the ions will be collected or created somewhere in the center. But more important is that the electrons, because now they are not killed at all, so they stay, they resemble like as if gamma would be 1. So you would see that your Paschen curve, it's more like the optimum. You can never go further down because gamma is already 1. That means that it's every hit of every electron when it is produced will stay in the plasma and create more and more electrons. Typically, they could mean that the Paschen minimum for the RF is roughly, so gamma 0.0 is quite typical, and you can see that the minimum is around 7 times less for the same electrode distance. Good. And now we have talked about a lot of collisions, etc., and that the Paschen is ignited. Now we have to say, so what is now exactly generated by this inelastic collisions? Now, well, of course, one of the most self-evident features is that it glows. So the plasma discharge glows. This glow is just due to the relaxation of excited molecules. That is the inverse of the excitation process. So in the excitation process, the transfer of energy to the bound electron enables the electron to jump to a higher energy level with the atom with the corresponding quantum absorption of energy. Well, you can also look at it and use the energy times the wavelength of your sended excited level, so your photons, and this is common physics know-how. That means that if you see, for instance, for fluor, we see a line around, we see that the plasma is glowing around 704 nanometer. We can calculate then what would be the energy that is needed over there. And all these colors in the optical spectrum are between 3.2 electron volt and 1.7 electron volts. This is also what we see later on, that this is indeed the excitation level, and that is going to be close to the most probable energy of your plasma, so the temperature, the electron temperature. Now assume that an electron is at rest in the plasma at T is 0. So then the radio frequency power will accelerate the electron and it will gain kinetic energy while having elastic gas collisions. But after the energy reaches the excitation level, the electron will have a high probability to drain all its energy in this excitation. So once an inelastic event has happened, it must start all over. So they are back to zero, and they again have to gain energy from the RF source. So consequently, most of the electrons will have a temperature below and close to the excitation. Therefore, mild discharges, and I define now mild discharge as taking here as a plasma just above or maybe on top of the breakdown voltage, so of the Paschen curve. They will have electron energies typically between 1 and 3 electron volt, and because that's where we could see that it's glowing. Now the Maxwell-Boltzmann PDF has its maximum located, therefore, at this specific excitation level. Of course, the more energetic electrons will cause also dissociation, so that creates radicals, and ionization. But more important also here is that when the applied power is increased while fixing the pressure and gap, the electron temperature will increase. So if we are not going to be mild anymore, the electron temperature will go up. We come also back to that one after the break. Good. Now, dissociation and recombination. Take a little bit. So the normal result of dissociation is an enhancement of chemical activity, since the products are usually more reactive than a parent molecule. Now, such enhancement of activity is used, for example, to oxidize photoresist in the plasma etching process using O radicals. Or in the case of SO6 in plasma, it is the fluorine radical being produced after dissociation that etches silicon spontaneously. Now, it is possible that dissociated species will recombine and lose their activity. For example, when the dissociated product drop on a third body, such as the reactor wall, they will recombine and give away their excess energy in the form of heat. So they are produced, but they are also easily lost. And now the most important one, of course, for the plasma, the ionization. This is where the process in which a primary electron removes the electron from an atom. It produces a positive ion and an extra electron, and it's called electron impact ionization or simply ionization. Now, this is the prime feature of discharges, with perhaps as many as 10 to the power 18 electron ion pairs being produced per second. Well, the ions are even more unlikely to survive the encounter with the reactor walls, as this wall is often conductive and therefore will provide the necessary electron that will neutralize the ion. Here you see a little bit the list of ionization levels of different molecules. Let's go now again back to SO6. We will talk about it quite a lot because that one is our prime gas to etch silicon, and we would like to have this as a kind of an example. We can find in literature that for excitation, the electron temperature is close to 1.75 electron volts. And we could see that the plasma glows around 704 nanometer. You can also find that the dissociation, so that's the moment where SO6 is broken into SF5 and F radical, it's roughly around 7 electron volts. Which means about 4 kT electron temperature at Tx for the excitation. Then for ionization, it's about 15.7 electron volt, or 9 times the value of the excitation. Now, we already talk about that if we have a mild plasma, that most electrons will lose all their kinetic energy when they pass the excitation threshold. That's around 1.75 electron volt. And we see now here, so that is at gamma is 1. But now if we now look, this is roughly 9 times for the energy. So the velocity or the speed, the most probable speed, is then here 3 times, because we divide the speed by the most probable speed. What does it mean? So here, from this level, all these energies are sufficient for creating, so the velocities of the speeds of these electrons at this side are able to create excitation. Dissociation only happens at 2 times. So at the number of 2 here, to have sufficient for creating radicals. And for the ionization, we also saw here is from 3 upwards. So that is here then the question. Consider now that we have this example, this envelope peaking at the excitation level. Now, can we now arrive an expression for how many electrons have enough energy to reach the excitation level and ionization? And can we give an expression for the ratio? Well, we go back to this normalized function. And yes, what we just said, what we have to do, we have to integrate this function, this normalized function, for the excitation level from 1 up to infinity. And for the ionization level, we have to integrate this capital gamma from 3 to infinity. If we do so, you would see that the number of radicals is roughly 10 times the number of photons that are produced inside your plasma. And the ions are, let's say, even 100 times less than the radicals and 1,000 times less than the photons. That's important, that lets we see that for a normal mild plasma, if you don't do too crazy, then typically the number of radicals is totally outperforming outnumbering the number of ions by a factor of 100 typically. Here's the proof. It's a lot of error function and so on. I just wrote it down completely so you can follow it, but do that later on, I would say. But so that's how we prove this number here. Now we go, and we are coming close to a break. We talk a little bit now about what we call the Debye lengths, because we already knew now that plasmas are conductive and respond to local changes in potential. Now, the distance over which such a potential perturbs a plasma is known as a self-shielding or Debye length. So if a piece of charged matter is inserted into a plasma, a cloud of positive ions will surround an object when the object is negatively charged. And a cloud of electrons will surround a positively charged object. Now, no electrical field will be present in the bulk of the plasma outside these clouds. And now this phenomena is called Debye shielding, and the clouds are called sheets. Now, the Debye length just gives us the thickness of the sheet in which the shielding is almost complete. So always within this sphere, you still have electrical fields which are still fooling around with ions and the electrons, but outside they don't. There's only outside of the sheet this macroscopic electroneutrality holds. And that is why the plasma is also neutral. It must be. How to find it? Well, this is derived from Poisson's equation. Please follow this link over here to find out that if you start with the Poisson equation, it's not really rocket science. It's easy to solve, but you need some efforts there. We can now then solve the maximum distance by which the charge may separate from each other before restoring force of the electrostatic field pulls them back together again. So this is was the Debye length. It is, we can find that after solving the Poisson equation to be the square root of this function, what you can see here. Now, in the case of a closed discharge, if we fill in numbers, which is typically having a density of 10 to the power 10 per cubic centimeter of ions and electrons, and our electron temperature is around 2 electron volts, then we find that our Debye length is around 0.1 millimeter. That means that in this case, if let's say the gap of your plasma would be 10 centimeter, it's significantly smaller than the dimension of the discharge tube. And that's important. So only when this is true, when lambda d is much smaller than the dimensions, then we can consider it as a plasma. So this criterion, of course, it has a high density of electrons, plus this one is that the ionized gas is a plasma. Good. Now, knowing this, let's see what happens with these ions, because we can see now that we have ions and electrons, and they, when you have something which is negatively charged, the ion will be attracted by it, but it will not necessarily hit it. And then you would get a situation where maybe you have here a positive charge, and the electron, let's say, is accelerated towards this positive charge, but it misses it, the ion. Then it will continue, but then it will be pulled back. at t is 2, at t is 1, but then it accelerates again where it comes to this close to this positive charge, let's say at t is 2. And then it does it in the opposite direction. So all the time now, if it doesn't hit, the electron might be swirling around this ion back and forth and back and forth. Well, we can calculate how much that will be, because these electrons, they have an energy of kTe. So let's say half times the mass times the electron speed squared. If you fill in that number in our just arrived the barrier length, we will see that this back and forth and back and forth, that's an oscillation which has this omega, capital omega, of the electron speed divided by the barrier length, and we fill it in, and we get the square root of nq2, or charge to the power 2, divided by m times the vacuum permittivity. If we now again calculate here, so fill in the numbers, then we would see that typically the oscillation of the electrons is much higher than for the ions, since the electron mass is very small. So for a plasma density of between 10 to the power 9 and 10 to the power 12, this would mean that our frequency of oscillations is between 0.3 and 9 gigahertz. And the much bigger SO6 molecule ion would resonate or oscillate between 0.6 and 18 megahertz. That difference is because we can directly calculate by taking omega pi over omega pi. It's the square root of the mass of the ion divided by the mass of the electron 500 times. Well, if you now look at these numbers, this is why the arrived power sources are typically operating at 13.5 megahertz, because only here at that frequency, the electrons are able to follow that frequency, and they get hot because they gain a lot of energy, but the ions cannot. They cannot respond to it. It's going too fast for them, and therefore they stay cold. So this is the basic idea. And as you can see, we would have here now a 5-minute break, after which we will finalize the fundamentals of Paschen. Thanks, and we meet again in 5 minutes.
Thanks, Henry. Yeah, everyone, please be back in 5 minutes.
Shall we continue again?
Sounds good.
Yeah, okay. So break is over. And now we come to let's say, another very important aspect in plasma etching, and it's the plasma to floating potential. It's about that, let's say, inside your plasma there are biases, voltages created which accelerate the ions, and that is going to be the driving force for reactive ion etching. Now first, let's say, consider that we immerse an object into a discharge. Now initially, more electrons will flow into the object by a factor of, we just calculated that before, roughly 3,000 times, because the flux of electrons is just 3,000 times more. That means that the object will charge negatively with respect to the bulk of the plasma. But then subsequently the positive ions will be forced to this negative object and surround it until it balances the negative charged object. That's the so-called, we just called it the bias shield. Here. Now, the plasma body is virtual electrical free, equipotential and neutral, and that's the so-called, after this operation, plasma potential. But similarly, we can associate a floating potential with the isolated object, which is always negative because it got a lot of negative charge in the beginning with respect to the plasma. Hence, after sufficient time, an equilibrium will hold where only electrons that enter the sheet from the plasma with kinetic energy more than this potential barrier, that will reach the object in perfect balance with an additional current of positive ions, because it should be in equilibrium. So that means that after a while, instead of the initial 3,000, it should be 1. That's important. Now let us start, we try to calculate. Let us start first with the general case where the plasma is composed of negative and positive ions. We call that hot thermal plasmas, like the sun. And they have an ion temperature for the ions of T minus and for the ions T plus, respectively. We call these hot ions. Now, when an object is immersed, yet to be determined potential, we just talked about, will develop depending on which ion is providing initially the highest current. And we just found that this is the equation we have to solve. Putting that together, and if we now first assume that the negative ions are bigger, the current density than the ions, so that means that the ion temperature of the negative ions divided by their mass is bigger. If you look at this equation, then the ion energy of the ions, positive ions, divided by the mass of the positive ions. So the object then will become negatively charged and acquiring a negative potential with respect to the surrounding plasma. So when this is true, it must be not necessarily that the plasma to floating potential is bigger than 0, because the negative was winning. Now this charge will start to repel the next incoming negative ions. Yeah, as we just explained. So when they start to match. But now we have two equations which we can go and try to solve now to get this plasma potential, this plasma to floating potential. As the object becomes negatively charged, if you look at the positive ions, this current will be simply the current or the saturation current that arrives from the glow at the Debye shield. It cannot be more than that because that's the maximum it can reach. And they all are accelerated. So it means that this current, which is going to be our equilibrium current in the end, must be identical to the initial current. But for the negative ions, they're going to be repelled. And the current density follows exponentially the Boltzmann distribution. So it is the equilibrium current for the electrons will be, or the negative ions will be the initial current times the exponential of the voltage difference. Now we will reach equilibrium when these two terms are identical. And we also know in the glow that the density of ions and the negative and positive ions are the same. This will result then in that the plasma to floating potential will be this formulation, where plasma to floating potential is bigger than 0. Well, in contrast, if we would have taken the opposite, that the negative ions are current density is less, then it will be, of course, the opposite. Good, but this is a hot plasma, so this would be the result. Nothing fancy and nothing more than that. But now for hot mass, so the ion current is depicted so the ion current is depicted by the ion temperature. But for cold plasmas, the main negative species is the electron, that one is much lighter than the positive ions. And as before, we have to consider the shielding effects. But now it turns out that for a plasma having Maxwellian electrons at TE at the electron temperature, and the electron temperature is much bigger than the ion temperature, that the mean velocity at the plasma sheet edge is equal to the Bohm velocity. It will be proven now in the next slides. So here you see that the Bohm velocity is the square root of kT over mi. So it can be interpreted that the ions will leave the sheet with a drift energy identical to the electron thermal energy. So that's quite remarkable, because now the electron temperature and not the ion temperature that depicts the ion current. So previously for the hot plasma, the ion current was also depicted by the ion temperature. But now the ion current is depicted by the electron temperature. And that's, of course, funny, because the electron energy is much higher. And that's why this Bohm current can be huge. So we do the same for this situation, where we say that's okay. Now for the current density of the ions, we have to multiply unit charge with the ion density times the Bohm velocity. And that and then you can fill it in with the previous equations to be this equation over here. Whereas for the electrons, we still have to follow the normal line. This quarter, again, that is because electrons in the bulk are assumed to have a random isotropic Maxwellian velocity distribution. So that's why you get this statistical factor. And we had that before with the flux, that we have a quarter in front coming from the Maxwell-Boltzmann statistical calculations. But ions are directed already. So there's no statistics over there. So therefore, this quarter is gone. So now, how do we prove this? Is now assume that the positive ions, they can fall through the sheet region without colliding. So let's say that's first what we say. We say it's collision free, and there's nothing where they are eaten away or recombine. Now the ions are entering the sheet or accelerated by the field, and their density must decrease to ensure a constant flux. So because here the number is coming, they're going to move faster and faster, but because they are moving faster and faster, their density is also going down. Now, if this decrease is too fast, so if they would go more like here, that they go down very quickly here, and then the electrons would reach further, because also the electrons will penetrate inside the sheet. And this would create a negative net charge, which would then increase again the ion velocity. So it means that by default, this slowing down of the ions, so the Gurin density must be always going slower than how the electrons fall down their density. Now the stable solution occurs when the ions enter sheet have just enough initial velocity to ensure that the sheet remains positive. And that is now the Bohm velocity. Well, please, to get track of time, you can see, this is just, you can follow how you can calculate now, but this is the currents who are coming in from the sheet and how they fall down here while they are going to be in this dark space region. And all the energy which it gains is coming from this kinetic energy, and it should be identical to the potential energy it will gain or lose in this case. So the kinetic energy gains is typical the same as the potential energy lost. And you thus can calculate with this one step by step how in the final stage you can see that the Bohm current or the Bohm velocity is the square root of kT over me. Just at home, try to follow this one by one. It's in a way straightforward, but for considering time, I would like to continue. But so we prove now that the sheet potential for the cold discharge in first order becomes the plasma to floating potential becomes kTA over 2q times the ln of m mass of the ion divided by 2q, 2 pi times the mass of the electron. But this implies that there is a pre-sheet, because the ions which can penetrate should have a certain velocity, but it has to be happening already before that, and that's called the pre-sheet. And we already knew that the Bohm velocity was the square root of kTe over me. Well, you can see that means that the Bohm velocity is in fact directly connected to the electron temperature. So the kinetic energy here is half times kTe. So the potential change in the pre-sheet region is in this order of half times kTe. So that this is equal to the thermal energy of the electrons. So we have to add that one to the total potential, because the potential plasma is, let's say, about 0 over here. And there is still something here where it gains. So that is that we have to add in the previous equation for kTe, this one, we have to add this pre-sheet value. And we come then to this value over here. Let's fill in numbers, because now it's becoming more interesting. For the SO6 ion, now the ion mass is roughly 146 times, let's say, the mass difference between the atom and the electron. So the plasma to floating potential is, if you fill it in, roughly 5.8 times kTe over Q in electron volts. That means that the ions reach the surface will have an energy equal to that, what they needed to surpass the bond velocity, plus that they have gained in passing through the presheet, and it's around, you could say also 6 kTe. So that means that the ions will hit surface in the plasma environment severely. So even when they are only floating, due to their acceleration in the plasma presheet and sheet, in case of a typical electron temperature of, let's say, 2 electron volt, the ion energy can be already 12 electron volts. This is enough to break most chemical bonds. So even if you have a plasma without any, let's say, DC bias developed, there is still a lot of energy in the ions who are continuously hitting the surface. Of course, these will also create extra electrons, but the most important thing is that they are going to break chemical bonds and might even etch your reactor. Then, with some help of Lieberman from the old days, that although we think that or we say that the plasma is neutral as a whole, and one might expect that its density is uniformly distributed, it's not true, because ions are continuously leaving the plasma at its boundary, causing bulk diffusion. We know that, as we saw, that ions, when they go out of your by the bond velocity, when they go out of your plasma, when they hit the conducting surface over there, it will be directly removed from the total plasma, because the electron will directly merge. Now, suppose that the ion density in a reactor is zero. We can calculate this. This is a very nonlinear, tough calculation. Please go to the book of Principles of Plasma Discharge. But the main message is that around when you look in if this would be a plasma cylinder with an ICP, maybe, that the number of ion, the density in the center is, which is, or let's say from the edge with respect to the center, is about maybe 30 or 40. At maximum, it is 50%. Because at all the time at sites, it is losing for the ICP here, maybe at this side. But, and this uniformity is by default. I cannot do anything against it. Even at a very low pressure, it saturates to this value. So it's always about 40% or worse. What to do about this? So this is why you many times see either a set of magnets, fixed magnets surrounding the reactor, where these magnets are arranged like back and forth with north-south source nows always twisting around. In that way, ions who would like to move there, they come in these magnetic fields and they are curling backwards. So it's the Lorentz force who is pushing it back towards, let's say, the center of your plasma again. Another type would be that you just put a big electromagnetic coil around it, so then the magnetic fields are straight down, and again, the Lorentz force is pulling all the time or pushing back the ions to the center. Of course, also the electrons. But we would like to have the ions being trapped inside. So this would already increase or improve a lot of the uniformity. Of course, you can also make many little plasma sources where one is bigger than the other one, and that are maybe more modern versions, or where you can try to do it with the reactor design. Now let's go one step further, because we think all the time, let's say we have generated photons, we are generating photons, radicals, and ions. Now what happens if we, let's say, remove or flow the gases much slower through the reactor, so we're increasing the resonance time? Now, first of all, if we would, the simple one to see is the photons, because if we would have a reactor with a certain pressure and we would close the exhaust, so we just say keep the gas there, we know that for the photons, they will keep on being generated, because all the time the electrons will stay, will keep on hitting molecules. They cannot go away, but the photons are excited, and the photons are, now let's say the molecules are excited, and the photons are absorbed by the walls, gone again, and the new ones are generated. For the Radicals, though, it's a little bit different because when it's dissociated, a radical, so let's say SF6 is split into SF5 and F, due to the law of energy conservation, they just cannot simply remerge. Only when you have a third body, they can do that. So that's most likely the reactor wall, or maybe a silicon target which is etching away the radicals. So even though the chance that a kinetic electron will produce a radical in a single event, when the lifetime inside the reactor is sufficient, yeah, maybe all SF6 molecules will stay be dissociated after many electron collisions. So if you now would put in, let's say, SF6 with a silicon wafer, you can understand that the SF6 will be cracked into SF5 plus fluor, and maybe the fluor is eaten away by the silicon, but then it's still there, the gas, then it's still SF5, and that one will be then the next target for the electron. It could be going down to when you have a very long residence time, so it means that you almost not remove the SF6, that all the SF6 is used to create, let's say, to crack the whole molecule, and this is, of course, a very efficient way of using your SF6. Notably, of course, that the sulfur might start to deposit on your, let's say, wave. So it could contaminate your system. So be aware that you can do this by saying, okay, I'm making it more efficient, but let's say then at that moment, it could be that you are ending up with contaminating your reactor. So in a way, for a short gas residence time, we typically would see that the SF6 is split into SF4 plus 2F or SF5 plus F. And then silicon would react with fluor radicals into silicon tetrafluoride. But if you more or less, let's say, close the valve towards, let's say, the exhaust, like to the turbo pump, with a long gas resonance time, you might use all the SF6 and start to deposit the sulfur. But also for the silicon tetrafluoride, which is produced, it can go nowhere. So it can, again, start to deposit. Well, this is in a way also plasma-enhanced deposition. So it means that while you changing your reactor residence time, you might go from pure etching and slowly you're coming into equilibrium where the etching is more or less in equilibrium going to be with the deposition. But the deposition is, of course, not on your wafer. It will be in your whole reactor. So be careful with this. Well, the same is true for the created ions. They cannot simply merge with the colliding electron because the energy cannot be drained. But unlike the radicals, the ions are forced out of the plasma glow due to the plasma potential. We just talked about it and causing this non-uniformity. Furthermore, at sufficient high power input, most of the input gas might be converted inelastically, which means that no additional radicals and ions can be produced. So there is a moment where all the SF6 which is hit has created an ion, but there's nothing more. So you cannot create more ions, let's say, than a number of SF6 gas you put inside your plasma. So if you have sufficient power and you crack all the SF6 into SF5 or SF6 plus ions, that's where is your limit. We call this flow limited. So it is, and it is possible to estimate the rate constant K of all the individual types, so the production, let's say, of your species. But because of all these drains, third body deactivation and radicals and ions used for etching, it will probably cause a substantial difference in their actual density. So therefore, I say that typically plasma etch engineers, they must rely on a more heuristic approach, and that will be treated in, let's say, the next session for, let's say, in December. Now, one step back to molecular cross-section, because that could be very confusing. You might say cross-section is cross-section, nothing fancy about it, that cannot change. But that's not true, because if you look at that the electrons, when the electrons have an energy less than the ionization, the electron will not create ionization. It's saying more or less the same, that the diameter of your or your cross section of your ion is 0 when you are below the threshold, and only when you come above the threshold it will start to grow. That is these kind of typical diagrams you see again in Lieberman, where these curves are calculated, and sometimes really theoretically they can find it. They can find these numbers. The same is also true for excitation and dissociation. So that means that the cross section of, let's say, of the ions, that it depends on the electron temperature, because only when it passes by the threshold it will be getting bigger. And also the production is then a function of the electron temperature. Well, you can calculate now by looking at the number of species that are being eaten away from the plasma by the production. So, and that can be filled in directly. And using, let's say, previous calculations, you find out that your cross-section ion is in fact the formulations you see over here. So it's a number directly controlled by the molecule and the electrons, divided by the gas density and the effective separation that is calculated here. So that means that, say, the cross-section is a function of temperature and temperature alone. And that is important because it means that if you take this equation into a plot, then you will see that if you go down in pressure, here, for instance, is 10 millitorr, if you go to a lower and lower pressure, that in fact my electron temperature is going up. So before we said that for a mild condition, it's around 2 electron volt. Well, that's a mild condition is at the higher pressures, because at the higher pressures, the electrons will have just sufficient energy to go beyond the Paschen curve and come, let's say, to create a sustainable plasma. But if you go to a lower pressure, because only then, let's say, the collision cross-section of the ions is getting bigger and bigger, therefore, the electron temperature goes up drastically. Here we are at 10 millitorr. At 1 millitorr, it can be already 3.8 instead of the 2.2. That means that for at below 1 millitorr, it can already reach easily the 4 electron volt. And if you even go further and down to the very low values of, let's say, maybe 0.3 millitorr, it can go even up to 6 times it. And it could be 23 electron volts. So instead of the 12 before, it can reach huge amounts of energy, which of course will crack a lot of material. And it will start even to sputter. The same story here, you can also do it more intuitive. So if you have a plasma somewhere here, and it's already, let's say, having a certain electron temperature, let's say 2 electron volts. If you go now lower in pressure and we stay inside the plasma regime, then because it's at the lower pressure, the electrons are gaining much more energy. And that means, of course, when you go from the place where it was already a plasma and we stay inside the plasma, so we are not going too far here, then the electron temperature will go up. So at a lower pressure, because the mean pre-pass is getting much and much bigger, the electrons will gain much more energy, and that means on average the kinetic energy will be gained. So that's more like an intuitive explanation. But the previous one is really a theoretical one. What does this mean? So let's assume now that we are somewhere here in above the Paschen curve, so where we have the plasma just above it at position 1. I would consider this, when you are close to this line, we have a reasonable mild plasma. So we have now just enough breakdown voltage to crack down the molecules into ions and electrons. Now, if you go then down, we just said, then we are increasing the electron temperature. It can be here, when you go from, let's say, 10 millitorr to 1 millitorr, it can be doubling. And we just saw it. Now we can do again the same trick as before, let's say, because in a mild condition, we said this is roughly what the curve would be. So the maximum is around excitation. But now, because our electron temperature is much higher, it means that the maximum of my electron energy, or that electron temperature, is far beyond the excitation level, which could be somewhere here. If we double it, it would be half, it would be here. It means that the excitation levels now already are in the tail going in the upper curve of the Maxwell-Boltzmann, and maybe in this case, by coincidence, the top is at the level of dissociation, and we go further, then the ions, the ionization would be somewhere here. If you do again the same calculation, you will see that if you then integrate this function as before, that the number of ions with respect to radicals is becoming only a factor of 3 times. So before that, at mild conditions, there were, let's say, 100 times more radicals than ions. But suddenly, when you go only, let's say, 10 times lower in pressure, it could be that you really reach a place where the number of ions is approaching the radicals. It can never, of course, it will never surpass it, because this one is always above that one. But it's only to say that you can play around with the pressure to change, let's say, the ratio between these two. And that's, again, also very important in reactive ion etching, because these two are the ones who are causing, let's say, our final result. The photons are less important. It's only to remember that decreasing the pressure means that you also change the ratio. And then a last piece of the puzzle, and is because we have now created the plasma, we know a lot of potentials, and we know what kind of species are moving around. But although we know the plasma to floating potential, there's another one, and it's called the DC bias. And that one is, in the end, in the reactive ion etching world, also extremely important, because that's why you would normally write it down. What is the bias voltage? Because that one is the one you can measure. The plasma to floating potential, normally you cannot see, but let's say the DC bias is. I will explain how that comes to one point with respect to first the capacitively coupled plasma, the CCP, and after that including the ICP source. So an effective method now to describe the ion enhanced mechanism in a plasma is possible without the help of an electrical equivalent circuit. It has, let's say, 4 main units. It's a reactor which contains the plasma glow discharge, the RF power supply to support the electrons their kinetic energy. Then we have the antenna matching unit, or automatic matching unit, AMU, which matches the electrical impedance of the power unit to that of the plasma. And there's a voltage standing wave ratio, VSWR, measuring unit to make automatic matching possible. Now, with the help of this equality, it's possible to arrive at the way the self-bias develops, and we will now see how it goes. I first come with a very simple electrical circuit. It is, let's say, a resistance, a diode, or a rectifying element, and a capacitor, and here we have a power, let's say the RF source. If you have here a swing of the voltage across 0, and we would put it to this circuit, what will happen is that when the current is positive, the diode will just go, the rectifier will just take the current and directly to ground. So then all the energy will go crossing across the R and creating Joule heat. However, if it's negative, it cannot go here, and it will charge the capacitor until all the voltage drops across this one, and there's nothing coming to be on this resistance. So the end result of the output would be that if they are, if this is perfect, a perfect capacitor, perfect rectifier, Vmax will be simply pushing the whole line down at minus Vmax over here. So below, so if this is top plus 5 volts and minus 5 volts, it will be here at minus 5 volts. So this is a simple circuit. What does it mean? Well, now let's go first to the plasma. We already know that when an object that includes electrodes and walls is in proximity of a glowing conductive discharge, it will create a dark space around it. Well, this space, we already know that it will be almost without free electrons because they were pushed away from it. And therefore, that's dark space. So that was, let's say, inside more or less the sheet. It's considered to be an insulator. Also, because of the electrons, the lack of electrons in the sheet, there will be no inelastic collisions that occur that could create photons. This is the reason why it is dark, and because there are no electrons to create photons. But because there are no electrons anymore, our conductivity is gone, and we can represent that as a capacitor. So it's an insulating medium, and that's what you can see over here. A capacitor at the anode side, a capacitor at the cathode side. But initially, more electrons will pass and this space because they move much faster than the ions by a factor of 3,000. So therefore, we can add to this capacitor, let's say, an element which is showing this factor of 3,000. So here, this means that electrons can pass, but ions cannot. And so that is the result of that. Initially the electron current is much higher. But also inside the plasma, it is not perfectly conducting. So there's a lot of heat generated, a lot of photons are generated, and all that kind of stuff. So that we can represent by a resistive element R. And that drains the energy from the electrons and creating heat by the deactivation processes. So with this in mind, we can now model it as an electric circuit. So we have now this resistance. We have here a capacitor and a rectifying element at the anode side and the same at the cathode side. Now assume that the anode is much bigger, let's say 9 times bigger in area than the cathode. That would mean that this capacitor is 9 times bigger. If you now apply here an RF voltage, then we know that the reactance of the capacitor is 1 over E omega C. So it means that the bigger capacitor will create a smaller voltage drop, let's say, than a smaller capacitor. In this case, because it's 9 times, the difference is 9 times. So if the cathode is 9 times smaller, it will develop a 9 times bigger voltage. And that voltage now is rectified. So for that reason, you get here then 1 volt being rectified, and the other one would be 9 volts rectified. But because there's the power source, it would be normally, if you would do this, it would really not work. It would start to spark, etc. We need a capacitor in between to make sure that this -8 volt is not shortened by the power source. So that's why there is always a real, so these are, let's say, equivalent of your plasma, but this one is really inside your reactor. It's not inside the reactor, outside the reactor, after the power source. Normally, this one is inside the matching box, but we just talk about in a minute. But now, because we have here our plasma, we also know that, yes, initially, the electrons were going through this rectifying element, but we knew that there must be an equilibrium somewhere where the Bohm velocity is going to be identical to the diode. So we have to include now a current source for these with the Bohm current, which is supporting that current. Important here is again to see that even though we have here solely an RF voltage at the anode, and we might not see it, but the plasma, this potential here, +1 volt, is always also, let's say, hitting the anode surface. So it will still receive 1 electron volt. So this one will be receiving -8, and this one is still at 1 electron volt. Now the ions are drained from the plasma by this rectified RF signal, equal amounts to electrons. And they will follow during a brief period of the RF cycle to restore the plasma imbalance. That's more like here. So all the time when the RF is swinging, the electrons, as soon as they are again good enough, they will directly be going through this rectifying element. And in the rest of the times, the ions are slowly moving by the DC towards the anode and cathode. Now, typically, the plasma power is provided by a cathode by a power source having a 50 ohm internal resistance and a 50 ohms coaxial cable. This is to get the power supported. Otherwise, you get too much reflections and you might end up with burning your power source. So we need to make sure that my plasma, which is here, you can see a lot of capacitive and resistive elements, it should merge with the characteristic impedance of, let's say, our source, which could be 50 or 60 ohms. To do so, they put in this matching unit. And the matching unit is arranged in such a way that they completely compensate so that when you would look from the power source into the coaxial line, everything is staying at 50 ohms, the characteristic impedance of, let's say, the coaxial line. This to make ensure that all the power goes and nothing comes back. Then a phase and magnitude detector is connected to it because that one can measure by a little coils wrapped around the coaxial line together with some diodes and electronics. It can see how much power goes forward and how much going backwards. What it will do is it will change the load and tune capacitor until all the power is being transferred forward and nothing is coming back. So it makes sure that there's no reflected power. That's this one. So this is measuring it and is tuning it until it is happy. So that's the antenna or automatic matching unit. So to conclude, the VDC or the DC bias is caused by the difference in capacitance between the anode plasma and the cathode plasma dark spaces. Of course, if these areas are the same, there will be no DC bias because they just well, they are the same because the sheet is the same. But it does not mean that there is no ionic impact, as we found out that the plasma potential can still be large enough to enhance surface reactions. So although we don't see the plasma potential, it can be still there. So in total, it is the DC bias plus the plasma potential that depicts the impacts. So that's here, let's say, a kind of a graph where you see now a total CCP system with all the units. So this is the plasma potential, which can create to the anode already the impact, but at the cathode, it will be plasma potential plus the DC bias, because the DC bias is you can measure between anode and cathode. This one we cannot measure, but it is there. So it's the total of these two, this part plus that part, that will hit my substrate. And because this one can be quite high at lower pressure, it could be that even more than the DC bias. So be careful by going to the lower pressure. It might be that you come up with the results you didn't expect. You say, but the DC bias was 0. Yes, but your plasma potential you didn't take into account. Now for the ICP, and we are getting closer to the finish. Well, because there's a coil wrapped around it, the hot and the cold side of the coil are the same. So it means that there's no anode and cathode in that sense. And the sheets are identical. It means it cannot create a DC bias by default, but it creates, of course, a plasma. So it's in a way the same, but you can model that like a transformer, which is putting the power into your plasma. And now these two capacitors are identical. So it means that there's no voltage difference between this side and this side. You cannot call it anode and cathode anymore because they are the same. So if you call this one anode and that one cathode, you can also call this cathode and so it doesn't matter. That means that the ICP will never show a DC bias, but it will generate a plasma and it will generate a plasma potential. Now, let's see what does it mean for the total. And that means we are going to connect now the ICP. We are running an ICP and CCP at the same time. That's the most common way, which is, let's say, how let's say modern reactive INS systems are running. We had already this simplified model for the CCP, the capacitively coupled plasma, but now we know that the ICP is also create, let's say, putting this energy inside the plasma glow, so the body of the plasma. These two capacitors or sheets are different because the area is different, but these two are the same. So they are, you can model it now because they are sharing the same, and this is enough because this would then you can say, to make it even easier, that we say, okay, this resistance now is tuned by the ICP. And what it means, if you increase the ICP power, typically the resistance will go down. Or saying it differently, you will increase the number of free electrons and ions, you increase the ion density. So the ICP is increasing the ion density. Whereas if you do so, then still the CCP, because of the difference in these two capacitors, the sheets at anode and cathode, it will create the DC bias. So then after this, ICP is generating a high density of ions and radicals. Then the following step is that the CCP will extract these ions with energy, which is controlled by the CCP. So the CCP can be at a quite low power, so preferably much lower than the ICP, because if the CCP power source would be as high as the ICP power source, then this one would also change all the time your ion density, because that power generates also a plasma. So you rather have this one to be higher, like 10 times, normally it's 10 times more, so that the ICP is solely creating the ion density, and the ion energy now is then controlled by the CCP, because this one is the only one who creates the DC bias, and therefore extract the ions from this field. Good. This is more or less ending the story, and I will give a little conclusion on the fundamentals and a sneak preview for the upcoming lecture. So what we saw in the beginning is a lot about gas fundamentals, where we started with the Maxwell-Boltzmann. We could find out what is that about the temperature, the pressure, the flux, and current density, and we talked about the collisions and the mean free path. And with that one, we could go, let's say, more or less to the plasma fundamentals, where we started with plasma ignition. We could find a little bit more about excitation, dissociation, ionization. We could find the Debye length, plasma oscillations, plasma to floating potential. We could calculate the Bohm current. And with that one, we could even arrive at solutions for the electron temperature, which is more or less the prime feature of the energies which are, let's say, going to be in our plasma chemistry in our next lecture. And then with all these data, we could create a kind of electrical circuit model where we, instead of not only looking at the plasma potential, we also create a DC bias. And this one is then directly telling us what is the ion impact and can be yes or not at a certain material, which we will see in the next lecture. And we also learned in a way that although we have a lot of calculations, because a lot of unknowns still exist. So although we can know the production factor inside our reactor, we don't know exactly where it is losing all these energies. It can be heat, it can be photons, which are going away. Ions are collecting energy. We are still not able currently in these days to calculate beforehand what will be the edge result, what will be the total product. And therefore we would need still a more pragmatic or heuristic approach. And we will treat that also in the next lecture. That would be for plasma of S fundamentals. In the next lecture, I will talk a little bit then about using the fundamentals we learned today, talk about spontaneous, sputter, and ion and etch mechanisms. I will talk about etch chemistry. So what kind of materials do we want to etch, and can we etch them in the first place? I will talk a bit about, let's say, what kind of etch rates can you expect? What can happen? So what is about how straight and nice a profile can be? How do we deal with that one? I will going to talk a little bit more about a reactor in its own, how it looks like, so the turbo pump system, a plasma reactor, etc. Also a real software, how it looks like when you plan to when you are behind the machine, how it looks like and what will happen. And here's a little bit about the reactor itself and how all these things are, let's say, etching a typical material, in this case, silicon. And then with that, that day and the finish of that day will be where I show all kind of results from when you really are in control of your plasma etch system, where you can create pillars, you can control, let's say, what the profiles. You will see what we call scallops. You will see how we end up with very small scales down to the 30 nanometer level, where it is still so high aspect ratio structures. And we will talk about Bosch processes where we have let's say a cycle of SO6 and C4F8 gas and the core, where we have a cycle of SO6 and oxygen. I will explain that then. And if you do all things correctly, we will end up with many nice three-dimensional structures we can create in a single multi-step run for plasma. We can create a lot of funny stuff where we are in full control of the plasma. Good. I'm finished, and we are open maybe for questions. So this would be coming.
Thank you very much, Henri. That was
next time.
amazing.